Today we're going to look at relative masses as well as the mole, and we're going to start with the atomic mass unit. Now, the mass of a single atom is so small that it's almost impossible to weigh it directly. If we look at the mass of hydrogen, we can see that it's 1.66 times 10 to the negative 27 kilograms, which is very, very small. Now, atomic masses are therefore defined in terms of a standard atom, which is called a unified atomic mass unit. We denote this by saying U. Now, 1 U is defined as 1/12 of the mass of a carbon-12 isotope. Now, this is often called Da or Dalton. If we look as an example at helium, we can say that the atomic mass unit of helium is 4 Daltons or 4 U. Next, we're going to have a look at the relative atomic mass, or AR. Now, the relative atomic mass of an element is the ratio of the average mass of an atom of an element to the unified atomic mass unit. Now, the relative atomic mass is determined by using the average mass of the isotopes of a particular element. Now, the relative atomic mass has no units as it's a ratio and the units cancel each other out. Now, we can use helium as an example again. The relative atomic mass of helium would be 4.006, which is the average of all the isotopes of helium. Next, we have the relative isotopic mass. Now, this is the mass of a particular atom of an isotope compared to the value of the unified atomic mass unit. Now, atoms of the same element with a different number of neutrons are called isotopes. So remember, guys, if we have an atom with different amounts of electrons, then we have different ions or charges of that atom. But if we have different amounts of neutrons, then it's isotopes. Now, isotopes are represented by writing the mass number above on the left-hand side of the atom. To calculate the average atomic mass of an element, the percentage abundance is taken into account. We then multiply the atomic mass by the percentage abundance for each isotope and then add them all together. We then divide them by 100 to get the average relative atomic mass. This is known as the weighted average of the masses of an isotope. Then we also get the relative molecular mass, or MR. Now, this is the ratio of weighted average mass of a molecule of a molecular compound to the unified atomic mass unit. Now, the molecular mass also has no units because it's a ratio and the units cancel out. Now, we can calculate this by adding up the relative atomic masses of all the atoms present in one molecule. Now, when calculating the MR, the simplest formula for the compound is used, and this is also known as the formula unit. For example, silicon dioxide has a covalent structure. However, the simplest formula or the formula unit is SiO2, even though it is much larger than this. Lastly, we have the relative formula mass, also denoted by Mr. Now, this is used for compounds containing ions. It has the same unit and is calculated in the same way as the relative molecular mass. A good example of this is potassium carbonate. Let's have a look at how to calculate a few examples. Let's start with working with isotopes and working out the relative atomic mass. Now, let's look at magnesium. Let's say there's 3 isotopes. Magnesium 24 with a relative abundance of 78.99%, magnesium 25 at a relative abundance of 10%, and magnesium 26 with a relative abundance of 11.01%. Now, to work out the relative atomic mass, we are going to take the isotope and multiply it by its relative abundance. So we're going to take 24 multiplied by 78.99, then add 25 multiplied by 10, and add 26 multiplied by 11.01. We're going to then divide this by 100, and this will give us 24.32. Now here we do not use any units because it's a ratio and the units cancel each other out. Then we can look at an example on how to calculate the relative molecular mass. And we're going to use water as an example. Now the first thing that we're going to do is we're going to look at the relative atomic mass of the atoms found in water. Now hydrogen has a relative atomic mass of 1 and oxygen has a relative atomic mass of 16. Now we have 2 hydrogens, so we're going to say 2 times 1. And then we have 1 oxygen, so we're going to add 1 times 16. This will then give us a total of 18. Remember, this one also do not have any units as it's a ratio. Now we can look at the formula mass, and we're going to use potassium carbonate as an example because it's an ionic compound. Now again, we're going to look at the relative atomic mass first. Now potassium has a relative atomic mass of 39, carbon has a relative atomic mass of 12, and oxygen has a relative atomic mass of 16. Now we have 2 potassiums, so we're going to say 2 multiplied by 39. We have 1 carbon, so then we're going to add 12 to it, and we have 3 oxygens. So we're going to say 3 times 16. Now when we add these 3 together, we're going to get a total of 138. Now again, no units because it's a ratio, and in ratios the units cancel out. Okay, so now we can move on to the Avogadro's constant. Now this constant has a symbol of Na or L, and it's the number of particles that's equivalent to the atomic mass or the molecular mass. This can be for atoms, molecules, ions, or electrons. Now Avogadro's constant is 6.02 times 10 to the power of 23 grams per mole, meaning that 1 mole of any substance is 6.02 times 10 to the power of 23 atoms. Now 1 mole also has the same mass as the relative atomic mass of that atom in grams. For example, if we have 1 mole of carbon, then we have 12 grams of carbon. We also have 6.02 times 10 to the power of 23 atoms of carbon. Now we can apply this to a more difficult example, like hydrogen gas. So 1 mole of hydrogen gas is 1 times 2 because there's 2 hydrogen atoms, and this gives us 2 grams per mole of hydrogen gas. Then 1 mole of hydrogen gas is also 6.02 times 10 to the power of 23 molecules of hydrogen gas. But we can also say that 1 mole of hydrogen gas has twice Avogadro's constant, so 6.02 times 10 to the power of 23 atoms of hydrogen. And this is because there's 2 hydrogen atoms in the molecule.